now. All right, welcome everybody to today's Astroparticle seminar. We're happy to have a speaker today from the Institute of Astrophysics in Paris, Julien Froustey. He's doing his PhD there. It's going to be finished soon, if I understand correctly. Yes, so Julien works on topics related to neutrinos in the early universe, like neutrino decoupling and its effect on Big Bang nucleosynthesis, flavor oscillations, and primordial nucleosynthesis. And his talk today will be related to these subjects. It's titled Primordial Neutrino Asymmetry Evolution in the Early Universe. So Julien, thank you for being here, and please take it away.
Thank you very much. So now you should see my slide. It should be okay.
Yes.
Okay, so great. So yeah, thank you. Hello, everyone. As you said, I'm a PhD student at the Institut d'Astrophysique de Paris. I'm defending in June, and I will present our latest work with my supervisor, Cyril Pitrou, on primordial neutrino asymmetry evolution in the early universe, which led to this paper recently published in JCAP. So to give really the big framework in which I will be working on, I will talk a lot about the mega electron volt age. That is the time in the evolution of the universe when the temperature was about a mega electron volt or 10 mega electron volt. And in those times, what was the universe made of? Well, it was made of an electromagnetic plasma containing charged leptons, that is muons, anti-muons, electrons and positrons, and photons. And they were all interacting through QED interactions. And aside from this electromagnetic plasma, there is the bath of neutrinos and antineutrinos, which are in interaction with the electromagnetic plasma through weak interactions. So there are two big events taking place in the electromagnetic plasma, which have big consequences on the evolution of the early universe. First, when the temperature goes below the muon mass, you have this reaction that is the muon-antimuon annihilation and percreation in the other way around, that can only take place in the direct sense, because if the mean energy of photons, that is basically the temperature, if that temperature is below the muon mass, then you don't have enough energy to create muon-antimuon pairs. Therefore, when the temperature goes below 100 mega electron volt, all the muons and antimuons basically disappear, and they transfer all their entropy to the photons, the electrons and positrons, and the neutrinos. Therefore, there is a global reheating, if you want, of all the species. But then when the temperature goes about 1 mega electron volt, there is what is called the neutrino decoupling. It corresponds to the moment when the neutrino interactions with the electromagnetic plasma become too weak compared to the Hubble expansion rate. You can, if you are in the Fermi theory that is valid for the range of energies we are considering, you can have the scaling of the interaction rate gamma and the Hubble rate, and you can see that the decoupling will take place at about 1 mega electron volt. So it means that below 1 mega electron volt, you can consider in a first approximation the neutrinos and antineutrinos to form a decoupled bath, the cosmic neutrino background, which has completely decoupled and does not interact anymore with electrons, positrons, and photons. But then if you go back to the electromagnetic plasma, what happened with muons and antimuons happens exactly the same when we reach the electron mass, that is 0.5 mega electron volt. So you expect a reheating of the photons, but not of the neutrinos. And that leads to a ratio, the famous ratio 11/4 of the temperatures between the final photons and neutrino temperatures. But actually, a key thing I have studied during my PhD is the fact that basically this temperature, 1 mega electron volt, and this temperature, 0.5, are very close. So you expect some overlap between those two events. And this will lead to some distortions of the neutrino spectra. Actually, the decoupling will be a non-instantaneous process, and some entropy of the electrons and positrons will be transferred to the neutrinos. So basically, there is a need for a very detailed study of this decoupling of all those processes to be able to compute precisely the relic neutrino spectra and its effects on CMB, BBN, and so on. So that's for the general picture. But on top of that, there is let's say, an extra layer of complexity, and it concerns asymmetries. So as we call it on the bottom of the slide, the asymmetry is defined as the difference between the number density of a particle and its antiparticle. So for the charged leptons, basically the electrons, there are really tight constraints on the asymmetries, and that's due to the baryon-to-photon ratio that we know has to be of about 10 to the minus 9. And so given this very small value determined by Planck, for instance, and BBN studies, I think, BBN studies, yeah, given that very small value, we can completely neglect that asymmetry. However, when we look at neutrinos, for instance, take their equilibrium Fermi-Dirac distribution, there is a priori no constraint on that chemical potential, because that constraint for baryons and electrons comes from charge neutrality, but for neutrinos, since they are neutral, there is no constraint a priori. So that's why we need to look at what, if we put initial chemical potentials, if we put initial degeneracies in the system, how it will evolve and how we can constrain those asymmetries thanks to our measurements in BBN and on CMB. So to understand, for instance, how BBN can deliver a constraint on the asymmetries, let me walk you through very basic BBN. So at the time of BBN, about 1 megaelectron volt, this is the composition of the early universe, and now, from now on, I mean, in that discussion, I don't need to consider the muons and antimuons. I discussed the photons and the lepton part, but there is also a baryonic part with neutrons and protons. But since given the baryon-to-photon ratio, what you can do is to study the evolution of photons and leptons, and once you have this background, if you want, you can study the evolution of baryons in this background of many leptons for one baryon. So Big Bang nucleosynthesis corresponds to the formation of light elements during the first minutes of the universe. And the basic example, the first light element that is produced is deuterium. Deuterium is produced through this reaction, the association of one proton and one neutron. And the reverse reaction is the photodissociation. Basically, if you have a bath of photons with high energies, basically you expect energies larger than the binding energy of deuterium, these photons will destroy the deuterium, and you will not be able to produce sizable quantities of deuterium. However, given this very large value, very small value of the baryon-to-photon ratio, even if you have an average energy of the photons that is much smaller than the binding energy, you will still have many photons in the tail of the distribution. When I say many, it's compared to the numbers of deuterium. So many photons that will destroy the deuterium. So that's why the significant start of a nucleosynthesis cannot be before 0.07 megaelectron volt. So you produce deuterium, and then there is a whole nuclear reaction network. I just put here the first reactions that leads you to heavier and heavier nuclides. For instance, I just put here as an example, 2 ways to produce helium-3 and 1 way to produce tritium, starting from, for instance, you take 2 deuterium and it gives you 1 tritium plus 1 proton. So if we were, if we were completely at equilibrium, we would reach at some point the most stable element, that is iron or nickel. But remember that in the early universe, in the evolution of the universe, the temperature is decreasing. So at some point, these nuclear reactions cannot maintain everything at equilibrium, exactly like neutrino decoupling. So there will be a freezing out of interactions, and we will, I mean, the element that will be mostly produced will be, in fact, the most stable element, but among the light elements. And among the light elements, there is a peak of stability for helium-4 due to the magic numbers in neutrons and protons. So there is this peak of stability, and it's mainly helium-4 that is produced. So now I can discuss where neutrinos intervene in that process. First, I talk about the freezing out of interactions. So that involves definitely the Hubble rate. And I recall that in the Hubble rate, through Friedmann's equation, enters the radiation energy density, so the neutrino and antineutrino energy density. And then, if you look at the neutrons and protons, before the start of nucleosynthesis, there is an equilibrium between neutrons and protons, equilibrium that is set by this ensemble of equations. And you can see that the electronic neutrinos and electronic antineutrinos distributions will be involved. So if you add chemical potential, so if you change the relative distributions of electronic neutrinos and electronic antineutrinos, you will change the neutron to proton equilibrium. And so you will change the whole nucleosynthesis. And then if you add a chemical potential, it will change the energy density, so you will change the Hubble rate. And that's how including primordial asymmetries will have some effect on BBN. So when you do a combined analysis of the BBN and CMB results, taking into account what I said, you use a BBN code basically. And if you put the same chemical potential for all the neutrino species, this is the constraint you get on the initial degeneracy parameter. So that is why, since given this value, this is why I will, in my work, I will discuss a range of degeneracy parameters that goes between 10 to the -3 up to 10 to the -1. But one very important remark I want to make is that this is done assuming that all three neutrino chemical potentials are equal. And this is done due to previous studies in the literature that show that basically whatever the degeneracies you put at the beginning, due to flavor oscillations, in the end, the neutrinos had the same degeneracies. And at the start of BBN, they had the same chemical potential. So that's precisely one of the points I want to study and that I will present right now. So that's another way. I want to compute neutrino evolution through the mega electron voltage with non-zero asymmetries and see how what we get, I would say. And that's also because when I say most accurately possible, it's because in the last years there have been much progress done in the study of the equations that that govern neutrino evolution and how to solve them. So now, just before I dive into the results, some elements about neutrinos, but some particle physics that I will need. I recall that in the standard model, there are 3 species of massless neutrinos described by a left-handed Weyl spinor. And ever since the Homsteg experiment and all the issues related to the so-called solar neutrino problem, now we know, I mean, the most accepted solution is that there are at least 2 mass eigenstates that have a non-zero mass, and the relation between the flavor states, nu in, nu mu, nu tau, and the mass states is given by the PM&S mixing matrix. And so, for instance, if due to this mixing, if you start with an electronic neutrino and you measure, I mean, you let it evolve in vacuum, and you measure its flavor at some time later, then there is this flavor oscillation, and you might measure a nu tau or a nu mu with those probabilities. So that's for the mixing, and the frequency of these oscillations is set by the difference of the masses, and we have been able to measure through oscillation experiments those masses, but still we don't know what is the hierarchy of masses. That is, if the eigenstates are ordered as 1, 2, 3 or 3, 1, 2, roughly. And on top of that, we don't know the mass scale. That is, is there a new 1 at 0 and new 3 at 0 or new 3 at 0, or all the masses up to some electron volt average mass? The only, what we know from the Planck experiment is we have a bound on the sum of the neutrino masses that is given at 0.12 electron volt. And a very recent bound from the Catherine experiment gives an upper value for the so-called electronic neutrino mass. That is an average of the different masses averaged with the coefficient of the PMNS mixing matrix, and that bound is 0.8 electron volt. So for what I'm interested in, that is neutrino evolution in the early universe, the fact that there is this flavor mixing will mean that I cannot describe the neutrino ensemble with just 3 distribution functions. Usually what you do is you take the distribution function that gives you the number of neutrinos of a given momentum and at a given position in space, and that's all. However, due to this mixing, we will have to generalize this set of 3 quantities to a full density matrix with off-diagonal components that account precisely for what we call flavor coherence, that is the mixing, if you want. And on top of this, let me just mention that there is also the same for the anti-neutrino density matrix. And the main question is, how does this object evolve? Because if you've done some kinetic theory, you know that the distribution functions, they evolve through what is called the Boltzmann equation. So how do we generalize the Boltzmann equation for the density matrix? And there have been different works in the past to obtain this equation. I just mentioned here the perturbative expansion of Siegel and Raffold, perturbative in the Fermi constant, so in the coupling. Fully relativistic treatment through the closed-time path formalism by Blaschke and Cirigliano. And in our work, in a previous work, we have developed a method quite similar to the first one, but using a more, I would say, step-by-step method, extending the classical PBGKY hierarchy. Anyway, the equation we get is this one. This is what is called the quantum kinetic equation that accounts for the evolution of the density matrix. On the left, you have the time derivative and this term that accounts for the expansion of the universe. And on the right-hand side, you have different terms. So first, you have a vacuum term, a commutator of the mass squared differences with the density matrix. And this is the term that is responsible for oscillations in vacuum. Then you have a lepton mean field term that is a term that is here due to the interactions of the neutrinos with the background. So this is basically charged currents with electrons and positrons in the background and with muons and anti-muons in the background. And then you have the self-interaction term that involves the asymmetry. So you start from the density matrix, you integrate it over momenta, so it gives you a matrix of the densities, and you do the same for the antineutrinos, and you take the difference, and that is the asymmetry. So that's the self-interactions. And finally, you have the collision term. So the collision term, it accounts for all the processes that change the momenta of neutrino, so scattering with the charged leptons, annihilations, and all the self-interactions, so scattering among neutrinos and antineutrinos, annihilations, etc., etc. Let me just briefly mention the assumptions I do in this calculation. First, I assume isotropy and homogeneity. So that's why rho only depends on the momentum, the momentum amplitude, and not on the position. I assume only standard model interactions. I don't put a CP phase in the PMNS matrix, but I could refer to our paper to show that it doesn't change anything. And finally, if you want a precise calculation of the neutrino evolution, you need to take into account that the plasma is not an ideal gas, so there are some finite temperature corrections to the equation of state, and we have included them, the most recent calculated ones. So just for the following, I will use some notations that I present right now. I introduced some variables that allow to account for the expansion of the universe. Basically, they are dimensionless variables that are used in the numerical code. So X will be the equivalent of a time variable, if you want. It's a proxy for the scale factor. And Y will be the momentum. And TCM, the co-moving temperature, is the temperature that goes as 1 over A, with A the scale factor. So when you do that and you put in all the prefactors right, there is the vacuum contribution H naught, the H lep for the leptons. I will call J the asymmetry contribution that appears in the quantum kinetic equation, and K the collision term. And finally, if I gather all the Hamiltonian parts except the asymmetry, I will call it V, but a common notation in the literature. And that is everything that would be left in the Hamiltonian if there was no asymmetry. So now, to make you understand what happens, I will take the example of a two-flavor system, not directly the three-flavor one, just let's take only two flavors that mix, and how do they evolve? So we'll take the example of nu mu nu tau mixing. So just to give you the values of the parameters. And so the main advantage of this two-flavor system is that it allows for a vector representation of the matrices. Basically, since rho is Hermitian, you can expand it on the basis of Pauli matrices, and this is how you can define a vector rho. I give you here the components, and one of the most important things is that the Z component gives you the difference between the mu mu and tau tau components. I say mu and tau because I said that it was a mu tau mixing. So once you use this representation, the quantum kinetic equations, they are rewritten like that. Just remember basically that the commutators become wedge products between the Hamiltonian and the density matrix. And I also write the equation of evolution for the anti-neutrino density matrix. And just note that the only difference is a difference of sign on V. So it's V plus J and minus V plus J. So once we have that, a question, I mean, it will be useful in the following. We can define the evolution of the asymmetry vector. So we just integrate the difference between rho and rho bar. And this is its evolution equation. Basically, A and J are exactly the same up to a prefactor. And so you can see in this evolution equation that you have the difference of collision terms, and there is only V that is left with a wedge product with the sum of the neutrino and anti-neutrino density matrices. So that's for the evolution equation, sorry. So now, if we want to understand what happens, let's look at what are the terms appearing in the quantum kinetic equation. So on this plot, I show you the order of magnitude of all the terms in the quantum kinetic equation. So let me walk you through it. In solid lines, I mean the orange and brown, you have the vacuum term, that is the ones proportional to the mass squared differences, and they grow as x squared. So you can see they grow as x squared. Then you have the lepton mean field in dashed lines for the electron positron in blue, and for the muons in green, and you can see what corresponds to the exponential decrease of the muon density in green. And then you have, for let's say average chemical potential, the self potential J in blue, and finally you have the typical value of the collision term in red. So let me just mention right now that when you will have the crossing between the vacuum term and the lepton mean field term, it will correspond to MSW transition, that is the transition between a lepton-dominated Hamiltonian to a vacuum-dominated Hamiltonian. That is true in the absence of the self-potential. So if the asymmetry were negligible, then you will, at that precise temperature, you will have the system which was dominated by the lepton contribution and would be now dominated by the vacuum contribution in the Hamiltonian. So, but one must, what I want you to notice is that all those values, if you look at the y-axis, these are the components of the Hamiltonian. And I recall that the eigenvalues of the Hamiltonian, they give the frequencies, the oscillation frequencies of the system. So you can see that when you look at the values, they are much larger than 1. And given the dimensionless parameters they have used, it means that it's much larger than the typical natural evolution timescale, that is the Hubble scale, of the system. Therefore, there will be some possible averaging of these oscillations that will be incredibly fast compared to the natural evolution of the system. And that is the idea behind this adiabatic transfer of average oscillations that I will present right now. So, as I said, the Hamiltonian components set the oscillation frequencies of the system. So for instance, take just this equation. I don't put the collision term, but it's exactly the same idea. So you have a very fast precession of rho around H. And since it is so fast, we can actually only observe the average of this precession movement. And then if the Hamiltonian evolves slowly compared to this precession, then a very accurate description of the movement of the evolution of rho is just to say that rho is constantly projected onto H, and then it follows the evolution of H. So that is an averaging of the adiabatic evolution of rho, hence the name of the approximation. And this approximation was validated in the zero asymmetry case, that is when the Hamiltonian does not contain the asymmetry part. In a previous work we did, where we computed the effective number of neutrino species. So when I come back to this plot, you will basically, the idea will be to say that since I can say that rho is projected onto the Hamiltonian, I just have to follow the Hamiltonian, and it will tell me how the system evolves. So if I discard the self-potential, at very high temperatures, it follows the lepton mean field, and then it will follow the vacuum mean field. And if, on the contrary, and that is what I'm interested in today, I include the self-potential, you can see that it will dominate a lot the evolution of the system. And for instance, for psi equals 0.01, you expect to feel the effect of the lepton and vacuum mean field only at very small temperatures. So now let me prove what I said, and let me show you how the system truly evolves with some animations. So in this plot, you will have in solid line the density matrix, and in dashed lines the anti-neutrino density matrix. In pink, you have the value for a small momentum, for a small dimensionless momentum, and in blue, you have the same for a large. And all vectors are normalized to 1. So first, let's assume that there is no self-interaction mean field, so there is no asymmetry in the system. So there will be, as I said, MSW transitions. So rho will follow its Hamiltonian, and the Hamiltonian will be at high temperatures along the z-axis. Since this is at high temperature, I recall the lepton part dominates. And then at smaller temperature, below the MSW transition, you will have an X component that is developed. So that's what we observe. First, there is the pink transition, and then the blue transition. And it's logical that the transition for smaller momenta takes place before. So you can see that there is no collective behavior. Every row evolves by itself, and that's all. If now we include a self-interaction mean field for, I put a chemical potential of 0.01, now what happens? You can see that the evolution is very, very different. There is a completely new phenomenology. First, there is a collective behavior. You can see that the pink and blue curves are completely superimposed. I mean, there is no difference between them anymore. And there are now some weird oscillation taking place at a faster and faster rate. There is this huge nonlinear effect of the self-interactions, and that leads, this phenomenon is called the synchronous oscillations. So if I plot it differently, this is the evolution of the neutrino density matrices, and in dashed lines you have the anti-neutrino density matrices. So you can see that when I plot the z component, there is this these synchronous oscillations. So independently of the value of the momentum, they are in phase, and this is true across the evolution. So how can we understand that? First, let me say that this is something that has been known for the last 2 decades and that has been studied, but we can actually revisit it with our ATAO approximation with this framework. This allows us to understand that phenomenon in a different way, and I will show you later that it even gives us, this is more interesting, some new results. So as I mentioned, rho is at all times projected and it follows its Hamiltonian. At very high temperatures, the Hamiltonian is completely dominated by the self-potential. Remember the blue curve. So rho will have this form. This is the vector with at high temperatures you have equilibrium distributions, and A is the unit vector in the direction of the asymmetry. Same for rho bar. So when you put that into the equation of, if you take rho minus rho bar, I mean, you put that into the evolution equation for A, and this is what you get. You have the new, you see that A, the asymmetry vector, evolves as with a precession equation, the precession frequency being given by the Hamiltonian for an average momentum that is typically pi, but an average momentum that is multiplied by what we call the slowness factor, because you can see that the smaller the chemical potentials, the slower the frequency. And finally, let me say that since A evolves precessing around this effective Hamiltonian, since all the rows are aligned with A, it means that all the modes will follow the same directions and will be precessing exactly like that. So the expected behavior as a summary of this first part, at very high temperatures, the little v Hamiltonian, so the part of the Hamiltonian without the asymmetry, it's dominated by the lepton part, so it's aligned with z. And A, the asymmetry vector, is also aligned with z. So everyone is aligned with z, nothing happens. But at some point, there is the transition, the MSW transition between lepton and vacuum domination for this average momentum, and it happens at a given temperature. So the Hamiltonian V will change its direction. Therefore, given this equation, there will be a precession of A around V. But since we are below the MSW transition, it's basically V is roughly H0, the vacuum Hamiltonian. So now you have 2 cases. First, if the transition between everyone around aligned with Z and H0 is abrupt, if this transition is very quick, then imagine that A is slowly, I mean, doing nothing, and suddenly you have a change of direction. It will have a large precession because its direction of precession has been brutally changed. On the contrary, if the transition is very slow, then A will be able to follow gently the evolution of V, and you don't expect much oscillations. Since the frequency, and this discussion of slow versus abrupt you have to do it compared to what? Compared to the precession frequency. Since the precession frequency increases with the chemical potential, you see that the faster the oscillations, the less you expect oscillations. So it means that if you have a very high frequency, we expect A to follow V. That's basically that. And if you have, on the contrary, a very small frequency, so if you decrease the chemical potential, then you will expect large synchronous oscillations. Now, I just want to have a small break and just ask if you have some questions arrive right now, and then I will show some more results. So if you have questions, now is a perfect time.
So you can just unmute yourself or raise your hand if you have a question in the audience.
So can you maybe formulate once again, what's the condition for, I mean, when there's difference between the usual treatment and what you are doing, when it is the most important?
You mean the approximation when we use it? Okay,
yes.
So we use it for two things. First, it will give us a way to understand what is happening, because since I say that the density matrix is constantly following the Hamiltonian, it's really a way to understand what is happening. But on the numerical side, if you want, I can take directly the equation, the quantum kinetic equation I showed, and solve it directly. That's what we did. But we also did it saying that we went to the basis. We changed the basis to go to the Hamiltonian basis, the matter basis. And then we diagonalized the density matrix in that basis. And we said, okay, the equivalence of projecting rho onto the Hamiltonian is to keep only the diagonal part. And once you do that, then you go back to the flavor basis, and you have, if you want, an effective equation that gives you exactly the same results. But since you only have to take to follow the three components of the diagonal instead of the full matrix, it's much faster. So you have a phenomenological side and a practical numerical side.
Okay, yeah, thank you. Thank you very much.
Okay, if there are no other questions, maybe I continue?
Yeah, thank you.
Okay, so now let me show you, well, basically the evolution of the system when I vary the value of the chemical potential of the initial degeneracies. So I write here on the bottom the values of the degeneracies, and you will have on the left plot the asymmetry for the two flavors, in green the muon flavor and in red the tau flavor. And on the right-hand plot, you will have in orange the normalized to one, it's the unit vector in the direction of A, and in brown, the effective Hamiltonian for the effective Hamiltonian for the average momentum. So we said that A is supposed to precess around V. That's exactly the behavior I described before. So let's look at what happens. Let me, in addition, mention that A is the Z component of A, for instance, is the difference between those two curves. Okay, so maybe I can do it like that. So at high temperatures, on the left, you have everything is aligned with Z, and so the asymmetries almost don't evolve. But then there is the MSW transition around, let's say, 12 megaelectron volt. And so you can see the Hamiltonian, the brown curve on the right, changing its direction from Z to something in the XZ plane. Since the chemical potential psi is quite high, the unit vector A is able to follow V pretty well. And then the precession has a small amplitude. And that's what we can observe here. You have some oscillations, but they don't have such a large amplitude. Let's now decrease the order of magnitude of psi by 1 order of magnitude. Let's take psi equals 0.01. Then for the Hamiltonian, it's exactly the same, but for A, it's going to be very different. You can see that A did not follow the Hamiltonian and then slowly starts to precess around V. So you have large synchronous oscillations, what you can truly see on the left-hand side of the left-hand plot. And then one thing I did not mention is that given all the prefactors, the frequency is increasing with time. And that's why you can see the acceleration of the oscillations. So fantastic. Let's decrease. Let's go all the way below, down to 10 to the minus 3, since it was the bottom of the domain of values I wanted to explore. And so now what we expect is a frequency to be even smaller. So we expect really the Hamiltonian to go to do its full MSW transition, and A to slowly start to do the synchronous oscillations. And that's exactly what we observe. And then it will precess around the Hamiltonian. But however, what we observe is it stops and it goes backwards, which is, I would say, a surprise, because it's not, it is not part of our equations. In our equations, we expect a precession around V, and that's all. So this back and forth is a new behavior that we need now. I will now present, explain and understand. So actually, the key explanation is the fact that we need to take into account the misalignment, the tiny one, between rho and rho bar. Or if you want, we need to take into account the fact that for small chemical potentials, when I showed the curve of the orders of magnitude of the components of the Hamiltonian, the self-potential really dominates, but it dominates less, and the mean field will start to have some effect. And basically, if actually the true form of rho and rho bar are these ones. And so if what I do is that I assume that V is still very small compared to J, but I will do an expansion of the unit vector in V over J. And so when you take the first order, what you get is exactly the same. You get a precession equation once again, but with a next to leading order term in the frequency, and then next to leading order contribution, it has this form. So it leads to a frequency that goes as x to the power 6, instead of x to the power 2. And also, since there is a 1 minus this term, there is a possible cancellation of the leading order and the next to leading order term. And that's exactly what we had before. We had a precise value of x for which the two contributions canceled. So the frequency was temporarily 0. And then the next to leading order contribution was dominating on the previous plot up till this back and forth. It was let's say, a leading order contribution that was dominating, and then it was the next to leading order one. So, so that is a new result of our paper, and we discussed it more, checking really the values of the frequencies and so on. But I will stop here for the description of the frequencies and talk now a bit about the effect of collisions, because up until now I did not discuss, just to focus on the phenomenology of synchronous oscillations. I considered cases without collisions. So now what happens when I include the collisions? The fact is, the true collision term, so if I put really the interactions of the system, like the weak interactions, the standard model of interactions of the system, then the collision term you get is almost transparent to nu mu nu tau oscillations. That is for one reason: the muon density is completely negligible in the range of temperatures we're interested in. So basically, nu mu and nu tau have the same interactions. So if you have an oscillation, a mixing between nu mu and nu tau, the collision term does not really care, if you want. So that's why, basically, if you put, if we add the collisions, it does not change the behavior with regards to the synchronous oscillations. However, if you had put a damping approximation, this can be very different. And if now I look at the, if I change the two-flavor system, instead of nu mu nu tau, I look at a nu e nu mu system, you have on these two curves in solid lines, what happens, I mean, yeah, in dashed lines, you have what happens when we do not include the self-interaction term. So you see that there are no synchronous oscillations. So let's not look at that. Let's look at the solid lines. The solid lines are the true evolution. So you have the synchronous oscillations. And on the right-hand side, you have the evolution. Solid lines are the same with the self-interactions, but with the collision term. And you can see that there are no oscillations anymore. And this is because due to the charge current processes between electronic neutrinos and the electrons in the background, which does not happen with a nu mu or nu tau, then there is a preferred direction, if you want. The collision term will specifically prefer the electronic neutrino, will specifically impose a certain direction actually in the flavor space. So it will completely dump these synchronous oscillations, which we can truly well observe here. But the thing is, we need to be very careful and use the true form of the collision term. Because if you use a damping approximation, which was done in the previous studies of asymmetry evolution, basically damping approximation consists in taking that approximate form. You just have a set of coefficients, and you put all these coefficients in front of the values of the density matrix, and this is your collision term. It is extremely convenient from a numerical point of view. It can be justified for some cases, but in general, it's not fully justified. And in particular, we computed the evolution of the system in exactly the same setup as in this paper in 2002, which used the damping approximation, and we use here the true collision term. And you can see that, so look at the solid lines, that the damping term really overdamps the synchronous oscillations. It completely kills them, while actually, for the reason I mentioned, that is the fact that the collision term is almost transparent to nu mu nu tau oscillations. This is the evolution we have, and it's much more subtle, and actually due to these oscillations and the fact that it's not reduced to zero directly, it can have some effect on the cosmological observables, and that is something we need to study. So now just one slide to give you, because if I wanted to discuss about the three-flavor framework, I could talk about it for hours, because there is a whole new range of parameters we can explore. So I will just briefly show that there is almost everything I showed before that takes place when now you put the three flavors. So in solid lines, you have the full resolution, and in dashed lines, the resolution, the solution of the equations, if I don't put the mean field self-interaction term. And so first, you can see that we have indeed synchronous oscillations that take place. And in the end, when you look at the final asymmetries, the values are different whether or not you included the self-potential. And that is very important, because one conclusion of the previous papers were sometimes, okay, if all the asymmetries are equilibrating, then why bother using a full code with the self-interaction mean field that is nonlinear and so on? Let's just use the code without the self-interaction mean field, and it will give us the right result. Actually, no, there is a, I mean, at the scale of the differences here, it gives a very wrong result. And for much more information on the three-flavor framework, I invite you to refer to our paper. So that leads me to my conclusion. We use the what I call the ATAO approximation. We extended it to the case with primordial asymmetries, because before we only used it in the context of standard neutrino decoupling, so without asymmetries, and that previous case led us to this new benchmark value for the effective number of neutrino species, a result that was confirmed by a different team. So that's the new value you can find in the particle data group review, for instance. And with this new study, we recovered standard results with a different insight, and we also uncovered new features like the faster regime, the next reading order regime that we called in our paper the quasi-synchronous oscillation regime. What I mentioned when I answered the question in the talk was the fact that with the ATAO approximation, we have less variables, so a faster code, but it's still very accurate. For instance, in all the two-flavor systems I showed, if you put the quantum kinetic equation solution and the ATAO solution, you cannot distinguish between them. Then I showed, I hope I convinced you that we need to be careful with what we do with the collision term if we want to capture really the correct behaviors. And finally, we have done the first three-flavor calculation with the full collision term. And this leads us to coming exciting work that is the exploration of the parameter space. And on that, I thank you.
Thank you so much, Julien. It's very comprehensive. I'm sure there are questions from the audience at this point. Shashank says thank you as well. Let's see. So maybe I'll start by asking just a general question. I'm wondering where you want to go next. So you pointed out a few directions where you could go, but what is next in your agenda?
So with that work, basically the first idea is to see using BBN results and the CMB likelihoods, for instance, how we can constrain the primordial asymmetries. Is it because the constraints we have up to now are assuming that all the asymmetries are equal, so we want to update that and look at, are there some physics that were hidden? Are there some? We have some new tools. We have some a more precise code. So we were like, okay, let's look at this and just try. Maybe the conclusions will be actually up to the precision we expect. There is absolutely no change, and that's completely possible. But we are still studying that. And for instance, just an example of what could be surprising. If you look at this, for instance. You had a perfect equilibration of the potentials, so everything was going to zero. But here on the right, and that is also due to the value of the theta 1,3 angle, you see that we have in the end a non-zero asymmetry for the electronic neutrino. And so the blue line here is not up to zero. And since the electronic neutrinos have a very, they are the ones affecting BBN, that kind of cases could change the values of the primordial abundances in a way that was not seen before. So we could have some changes, but we, as you can imagine, we have many checks to do, like be sure that it's not a, just a mistake or, I mean, so an artifact. So that is the kind of, on that topic, that is really the kind of things we are working on right now.
Okay, I got it. This is already interesting. And there is a couple of questions. So Irene, please just go first.
Yeah, thank you for the very nice talk. I wanted to ask you about what are the limitations of this ATAO approximation, or whether there are some contexts within the early universe where we cannot apply it.
So we haven't encountered such cases yet. I mean, yes, no. Let me rephrase. Actually, I think that if we include sterile neutrinos, there could be some problems, because when you have sterile neutrinos, at some point, they get suddenly populated, and so when you look at the Hamiltonian, it will then suddenly get it will vary very suddenly, and that very sudden variation would lead to a non-adiabatic evolution of the Hamiltonian, and in that case, we expect the ATAO approximation to break down. So basically, I think the sterile neutrino, the evolution with sterile neutrinos could present some problems. Otherwise, in the standard cases, I mean, if you, I don't know, since the main question is, does the Hamiltonian evolve slowly enough? And basically, the Hamiltonian evolves as powers of x, because it's just the natural expansion of the universe evolution. So apart from that, I'm not sure. I don't see directly a case in which it would collapse.
Okay, thank you.
And Ina had a question.
Yeah, thank you very much again for the nice talk. So in the collision integral, I mean, you were mentioning that you considered also this BBJKY hierarchies. Are there any difference between this and like usual quantum kinetic equations? Because the hierarchy should also account for some higher correlations, right?
So we reached the same equation in the end. That is this one, and that is because we truncate the hierarchy at the second order in the correlations, and we truncate it in a given way to account for the correlations that are built from uncorrelated particles. That is a sort of that's the molecular chaos ansatz. So I mean, exactly like the CTP formalism, that's the same. There is a hierarchy of equations, and they truncate it at some point. So it's always the only difference. I would say the main difference between our approach and the perturbative expansion is that we have the full hierarchy, and we have a very precise way to handle, if we wanted, all the correlations, and we truncate. While the perturbative expansion is more bottom to top approach, while ours would be, I would say, more top to bottom, if you want. But in the end, since our goal is to reach an equation, a quantum kinetic equation with two-body collisions, with correlations from independent one bodies, we reach the same equations, regardless of the method. I hope it answers your question.
Yeah, thank you. And one more technical question. So how do you solve the quantum kinetic equations? Do you use some specific framework? Because they could be quite stiff, right?
Oh yeah, so we use first we have a discretization in momentum. So you can use either a Gauss-Laguerre or linear grid. In the case of asymmetries, it's either with a linear grid. And then we use our code is working in Python, and we use the standard differential equation libraries that use an adaptive solver regarding depending on the stiffness. So either it's a backward differentiation formula system or Runge-Kutta. And so yeah, at very high temperatures, in particular, it's very stiff. So that's why so it's using basically BDF, but we do not handle it by hand, I would say. It's the LSODA solver.
Yeah, we use the same in leptogenesis here.
Okay, so that's the core of the, and oh yes, one very important thing is that we computed directly the Jacobian of the system, and we give it to the code because given all the equations, it's quite lengthy but straightforward to compute the Jacobian. And once we have it, it really speeds up by 1 order of magnitude in the grid size. So we compute the Jacobian.
Okay, yeah, thank you very much.
Thank you.
And there's one final question by Rasmus.
Yes, thanks for a very good talk. So there was a recent paper from Empress on a new determination of the primordial helium abundance. Have you seen that, and do you have any opinion on what? I mean, so the point of their paper is that they try to explain their observations with a large lepton asymmetry. So is this something that you think is interesting, or is it not to be trusted?
It could completely be. Actually, I've seen the paper but not read it. So it's about the helium-3 abundance, which is great because that's one of the abundances that we could not use up until now, since it was very hard to observe next to the helium-4. So I did not see that it was proposed to be a large lepton asymmetry. I mean, it could completely be, but I think that one of the conclusions as well is that if you want, the problem with BBN is always that whenever you want to change something, you destroy the values you have for deuterium and helium-4, which are very close to the ones expected. So I don't know if the large lepton asymmetry manages to change helium-3 without changing the others, but I doubt it.
Yeah, I also didn't read the paper in any detail, so I don't know.
Actually, what we want to do when we want to constrain the asymmetries is only to use deuterium helium-4, since that's the ones on which we have some good constraints. But it could be, actually, we could also look at helium-3. That's a good point.
Okay, thanks.
Thank you.
All right. I see no further questions in the audience. So, Julien, thanks again. It's
Thank
a very
you.
comprehensive talk. It's clearly state of the art, so it's always good to see this. And wish you also the very best for what's to come.
Thank you.
Thanks everybody for being here. We don't have a seminar in the next 2 weeks, but we come back after that. All right. Thanks, and see you soon. Bye-bye.
Thank you.
Bye.
Bye.